Today we are going to talk about the last properties of transition metals, which is catalytic properties. So, characteristics of transition elements. Previously, we have mentioned about the transition elements. They can form colored ions. Okay, we do have some exceptions. They have variable oxygen state. Again, we also have exceptions like scandium and also zinc. Today we're going to talk about the catalytic properties of the transition elements and also their compounds. Before we move on, okay, we have to know what is the definition of catalyst first. Catalyst, okay, is a substance that can alter the rate of reaction. Pay attention to the word we use here. We say alter. That means it can increase the rate or you can decrease the rate. But normally, okay, in DSE levels, okay, we focus on the catalyst. We say they will speed up the rate of reaction most of the time. That would be speed up the rate of reaction or increase the rate of reaction. But the key points, okay, another key points for the definition is, okay, they have to be without being used up in the process. That means the catalyst at the end, okay, they will be formed again. Okay, in the first half of the sections, they will combine with other things. And the second half, the reactions, they will be regenerate. Okay, in the process. So let's have a look. Okay, during the catalysis, okay, what really happenings in it? This is one of the possibility. When we have the transition metal or the compound, okay, it will first combine with one of the reactant. Okay, maybe the equation, okay, look like this: A plus B, okay, and then we give the product. So when we add the catalyst in it, let's say we have for example platinum, things like that. Okay, so the platinum will first combine with A to give an intermediate. So this intermediate is a complex, okay, is a you think about like a compound or things like that. Okay, and then this complex will then react with the other part of the reactant, say B. Okay, the intermediate will then combine with B. Then at this moment, okay, they will form products. And then inside this intermediate, we do have transition metal or compound, right? Then it will coming out again. So we'll say that, okay, the transition metal or the compound, they will regenerate it. So in the process, you find that we input transition metal and compound, but at the end, they also give out. So if I combine these two equations, actually these things can be cancelled out. Okay, so if we combine them together, you will find that the transition metal, they will cross out, intermediate, they will cross out, and then we have A plus B, and I have the product again. So we will call this transition metals or compound because it can be regenerated. So therefore we call that a catalyst. Okay, so catalyst normally will speed up the reaction, but we do have some to slow down the reaction as well. Okay, but most of the time you just consider like speeding up the reaction will do. Okay, let's have a look at an example. So right now we have iodide ion here, I minus, and we have peroxyl disulfate, which is S2O8 2 minus here. Okay. In the process, we'll use either iron 2 ion Fe2 plus or Fe3 plus. Both of them can act as a catalyst. Now, have a look at the first case without catalyst first. Okay. So you can see that right here. Okay, we will have I minus and S2O8 2 minus. They combine and then they will form I2 and sulfate. We expect in the process, okay, the colorless iodide ion combine with the colorless peroxyl disulfate, and then they will form iodine and colorless sulfate. So iodine actually is brown in color. So when they mix together, it will have something like this. So I just want to draw your attention. This one is a redox reaction because you can see that is changing from 0 to negative. Okay, this one, okay, you can calculate like S times 2 minus 16 equals to negative 2. So this one should be plus 7, right? Yeah, plus 7. Okay, while this one should be plus 6. Okay, so this one you can see a oxygen changes in the process, the ON changes in the process. So therefore, this is a redox reaction. But for this reaction to occur, okay, you have one criteria, which is I minus have to bond bound with the S2O8 2 minus. That means we have the iodide ion, 2 iodide ion, and also the SO8 2 minus. Okay, they have to come together to pass the electrons, okay, over to the others. Let's say iodide have to pass the electrons to the peroxide disulfide ions, okay, then they will have reaction. However, there's one thing, okay, stopping them from bombarding with each other, okay, that will be their charge. Because you see that, okay, all of them are negative. So the negative, they will repel each other. So therefore, is it easy for three of the ions come together and then they hit on each other in the right orientations with sufficient energy to carry out the reaction? The answer is no. So therefore, this reaction is very slow. Okay, you have to explain, okay, because, okay, it involves the collisions of two negative charged ions, two types of negative charged ions, okay? So not will be two types of negatively charged ions, okay? Because just say two ions, okay? Actually, it's not only two, okay? So you find that, okay, the negative and negative, they will repel each other, then they cannot carry out the reaction. So what we are doing right here, okay, we're trying to add Fe2 plus or Fe3 plus as a catalyst, and we're going to see how this iron-free ion or iron-to-iron help in the process. So let's have a look of case 1. So in this situations, we have add iron-free ion in it. So for the iron-free ion, after you add into it, okay, it will first react with the iodide ion. The iodide ion will pass electron to the iron-3 ion, and it itself, after losing the electron itself, will then become iodine. It is oxidized to get iodine. Fe3 plus, after gaining the electrons, will become Fe2 plus, and this Fe2 plus will then go react with the peroxide disulfide. So in this case, peroxide disulfide, the Fe2 plus, after gaining electrons, it will then pass the same electron to the peroxide disulfide, and then it itself, Fe3 plus, its Fe2 plus itself will then become Fe3 plus. After losing the electron, it will then become Fe3 plus, and the peroxide disulfide can then become 2 sulfate ion. Okay, so in the process, okay, you will find that where are the electron coming from? The electron actually is coming from the iodide ion. It first passes to Fe3 plus and then become Fe2 plus. And this Fe2 plus will carry the electron and then give it to the peroxide disulfide. So actually the electron is coming from the iodide. Okay, so you just you can see in this case, okay, we are having two steps of reaction, but in the process, okay, we actually don't have the collisions of the same charge particle, because in the first case we're having negative and positive, and the second step we have a positive to the negative, so therefore it will be easier for them to react with each other. So you just think about like this, okay, there is a boy and then he wants to pass a love letter, okay, to the girl, but actually the girl rejected. Okay, so the boy, what he is doing, okay, first of all he passed to another maybe handsome boy, okay, and then the boy can pass it to the girl. Okay, so the girl may be thinking that, oh, this one is from the boy number 2, okay, this is boy number 1. Okay, so maybe the girl think that, oh, it is coming from boy number 2, so we'll receive this one. So actually the letter is from boy 1, okay, but at the end, okay, it can pass to the girls. Okay, so something like that. Okay, so actually in the process, two of them, okay, they're opposite charge, so the collisions will be easier for them to do it. Okay, so for these two equations, if we combine them together, you find that Fe3 plus can be crossed out, Fe2 plus can be crossed out. So overall, actually, Fe2 plus and Fe3 plus, it does not involve, okay, in the final equation. And one more thing, you can see that, okay, we input Fe3 plus, but at the end, okay, Fe3 plus will be produced. So we say that this one is regenerated. Okay, remember we said that catalysts, okay, they must have not be used up, okay, in the process. So in this case, okay, we see that it will generate Fe3 plus. So Fe3 plus itself actually is a catalyst. Okay, it is a must. Okay, if in the process it doesn't regenerate, then we can't consider that as a catalyst. Okay, so In case 2, okay, this time, okay, if I add Fe2 plus, will it be okay? Actually, it is also alright. You put Fe2 plus here, okay, and then S2O2 minus, okay, at the back. So the Fe2 plus itself, they have electrons in it, right? So they will first give the electrons to the S2O2 minus, okay? It first give out their own electron first, okay, and they become Fe3 plus. And this Fe3 plus will then charged, okay, the electrons, okay, from the iodide. We will try to get the electrons out from the iodide to replenish the missing electron that they have, okay. So in the process, actually, it is the same, okay. You'll find that, okay, iodide ion will lose an electrons, okay, and then peroxide disulfide will gain electrons, okay. So this Fe2 plus, you see that at the end, okay, they will be regenerated again. So therefore, in this case, we also consider, okay, Fe2 plus as a catalyst. Okay, so combine the equation, we can see that, okay, exactly the same. Okay, because Fe2 plus can be eliminated, Fe3 plus can be eliminated. Okay, so this is how the Fe2 plus and Fe3 plus to carry out as a catalyst. We can have a summary, okay, using a diagram like this. Okay, you can see that iodide ion will pass the electrons to Fe3 plus, and the Fe3 plus will change to Fe2 plus, and this Fe2 plus will then pass the electrons to the peroxide disulfide, and then this one, after gaining the electron, will become sulfate. So we say that ion interconverts between +2 and +3. They will keep on doing this one from +2 to +3, from +3 to +2, okay. And in the process, okay, by doing this, or as a catalyst, they can speed up the reaction between iodide and peroxide disulfide, because at the beginning they are same charge, they repel each other. But now, okay, by with the help of the Fe2 plus, or the reaction, it eliminate the process having the collision of same charge particle, then the process will be much more smooth. So have a look of the class practice 49.4. Okay, so this one, these two are good questions, to be honest. Okay, these two are good questions, so you have to focus on that. Okay, so vanadium 5 oxide is used as catalyst in manufacture of sulfur trioxide in contact process, and the reactions, okay, it will happen like this. Okay, we put vanadium 5 oxide in it, okay, and at the end, okay, it generates vanadium 5 oxide. So the SO2 will first react with it to form vanadium 4 oxide, and vanadium 4 oxide will then combine with the oxygen to give out vanadium 5 oxide. Okay, so first of all, why is vanadium 5 oxide used in powder form in the reaction? Okay, so this is a very typical question. Why things is in powder form? Normally, powder comparing a lump, okay, the advantage is powder, they are small and have a large surface area. Lump, okay, they are a large piece, okay, the surface area is limited. Larger surface area, of course, it can catalyze the reactions, okay, more surface, okay, for the catalyst to occur, okay. So therefore the key points, okay, always goes to increase the surface area, more active site for reaction to occur. Okay, so we call that one active site. The surface is active site. So A good one. Okay, B is even better. Okay, why is vanadium 5 oxide not considered as catalyst if oxygen not added to the reaction? So you can see that, okay, right here, actually SO2 become SO3 already. Remember, contact process is manufacture of sulfur trioxide. If we just have statement 1 itself, okay, actually it would be good enough, okay, to see the product. But why we have to incorporate reaction 2? Okay, because we just have statement 1, okay, reaction 1. We found that the vanadium 5 oxide will become vanadium 4 oxide, and then that's it. This vanadium 4 oxide have no ways to get back to vanadium 5 oxide. So after we add this half oxygen molecule in it, you can see that, okay, it can combine with the vanadium oxide to form vanadium 5 oxide. So this vanadium 5 oxide can then regenerate, okay, after incorporate the oxygen in it. So we find that, okay, this one we cannot consider as catalyst because it doesn't regenerate itself, okay, in statement 1, in the reaction 1. So therefore, if we have add oxygen in it, vanadium 5 oxide can be regenerated. So we point out the key point is, okay, it can why it cannot consider as catalyst, because it cannot be regenerated with the absence of oxygen. No oxygen, it cannot be regenerated. Okay, so therefore a catalyst must not be consumed, okay, in the process. Okay, it have to be regenerated. Okay, otherwise, okay, it won't be considered as a catalyst. So this questions, okay, is a good one. So please revise. Okay, question number 2. Catalyzed reaction is found to proceed in 2 stages. Okay, so you find that this one and this one. Okay, in the process, you find that there is one chemical regenerating the process, that is cobalt hydroxide, cobalt 2 hydroxide. Is that right? There is a slightly difference in the number. This one is 2, this one is 4, but not a big deal. Okay, what you need to do is just multiply the first equation by 2. Then you have 4 right there, and then you can cancel out. Okay, so right now an equation for the overall equation. So you just multiply the first equation by 2, and the second one just by 1. Okay, and you just combine them. Then you will find that the cobalt 2 hydroxide will be eliminated. Okay, while the intermediate you can find cobalt 3 hydroxide. It can be also eliminated, because after that this one will become 4. Okay, so deduce which chemical species is likely to be catalyst. So the cobalt 3 hydroxide, this one is an intermediate. This one, okay, it is the catalyst. So this is the catalyst. Describe the action of catalyst. You stay in B. So the action, okay, what they have done. This is some things related to statement form to describe the process. Okay, so you just simply saying that, okay, the cobalt 2 hydroxide reduce the ClO minus to Cl minus. You just describe this one, reduce ClO minus to Cl minus. If you really can't say it's a reduce and oxidize, you can't think of that. Okay, no worry. You just basically say it react with the hypochlorite ion and turn it to chloride ion. Will be all right. Okay, and then you say that this one will turn into cobalt 3 hydroxide, and after that, okay, it will then, okay, turn back to the cobalt 2 hydroxide. Will do. Okay, so that's it. Okay, the process. So to summarize these videos, okay, first of all, we know that, okay, the transition metals or their compounds can have a catalytic process. Okay, compound, just as we mentioned an example like this one, like vanadium 5 oxide. The transition metal itself may be Fe2+. It's still an ions actually. Okay, but we have like platinum or the other things. Okay, so they can act as a catalyst. So you have to know that catalysts involve 2 features. First of all, they can alter the rate of reaction. Second, in the process without being used up. This one is very important. Okay, so during the catalysis process, normally the catalyst will first combine with one of the reaction, forming an intermediate, and this intermediate will then react with the second part of the reactants, and then most important part, okay, the transition metal or the compound, it will be regenerated. Okay, and the last things, okay, for point 4, okay, some reaction may be very slow. You have to know, okay, you have to realize why it is so slow. If it involves, okay, collisions of 2 same charged particles, like both of them are anion, then the ways that they combine with each other will be having less chance, because they will repel each other. Okay, lastly, okay, we do got very typical examples. We are using iron, okay, to catalyze the reaction between iodide and peroxide disulfate, and you can see that in the process, okay, the Fe2+ and Fe3+, they are interconvert each other, okay, by getting the electron from the I minus, by passing the electron to the peroxide disulfate. Okay, so this one is a typical examples. Okay, so you better bear in mind. Okay, revise that one. So that's all for this video. Okay, bye bye.